Hello students, today we are going to work on the first chapter of class 12's chemistry, and this chapter deals with the solution. But before we start this chapter, we are required to have some knowledge about a term called mole. Mole concept was there as a part of class 11 syllabus, so hope all of you know a little bit about moles, but still I wanted to tell you the meaning of 1 mole of a substance. Whenever we talk about 1 mole of anything, what we exactly mean is when we put 6.023 into 10 to the power 23 particles together. You know this number, 6.023 into 10 to the power 23. This number is called Avogadro's number, and it's a very large number because it has got 10 to the power 23, which is much larger than billion and trillions. If you have these many particles, what is the meaning of particles? If you have these many, let's say, atoms, then together the amount of that mass of that these many atoms together is called 1 mole atom. Similarly, if you have these many molecules, then we call that 1 mole molecule. So in order to have 1 mole of any substance, you've got to have 6.023 into 10 to the power 23 particles together. If you have these many electrons, we call 1 mole electron. If you have these many atoms, 1 mole atom. These many molecules, 1 mole molecule. But here in this chapter, we are basically interested in the molecules only, because most of the substances with which we prepare our solution exist in the form of molecules. So we'll deal with this 1 mole molecule. So what's the meaning of 1 mole molecule? 1 mole molecule means simply the mass of 6.023 into 10 to the power 23 molecules together. So if you have these many molecules, which is a big number, if you have all these molecules together, then the total amount is called 1 mole molecule. But there's another thing that we learned in class 11, and that is called gram molecular mass. So let me give you an example. You see, I've taken a molecule of water here. This is the molecular formula of water, H2O. So from this molecular formula, if you add the masses of all the atoms present here, that means 2 atoms of hydrogen and 1 atom of oxygen. You know what's the atomic mass of hydrogen? It is 1. So you're taking 2 atoms of hydrogen. One of them weighs 1, but there are 2 of them, so total is 2. And atomic mass of oxygen is 16. So I'll take only 16 because there's only 1 atom. So masses of all the atoms in this molecule together is going to be how much? 2 plus 16 is 18. So that's the mass of the molecule of water. It's known as molecular mass. From the molecular formula, by adding the masses of all the atoms, whatever we get is called molecular mass. Similarly, you can have some other molecules, like I'm taking molecule of carbon dioxide here, and this is the molecular formula of carbon dioxide. We can add the masses of carbon and oxygen atom present in its molecule and find its molecular mass. So carbon's mass is 12, oxygen's mass is 16, but there are 2 atoms, so the net mass is going to be 44. Okay, similarly, you can take another molecule. Let's say this is a molecule of a hydrocarbon called methane. So its molecular mass is going to be, carbon's mass is 12, hydrogen's mass is 1, but there are 4 atoms present in the molecule of methane. So the net mass is going to be 16. So this way, if you know the molecular formula of compound, we can add the masses of all the atoms present in the molecule to find its molecular mass. So everyone knows how to find the molecular mass. But if you take these substances, for example, I wanted to take water, but how much? Whatever is the molecular mass, same amount in grams. So molecular mass of water is 18, so I'll be taking 18 grams of water. Molecular mass of carbon dioxide is 44, so I'll be taking 44 grams of carbon dioxide. Molecular mass of methane is 16, so I'll be taking 16 grams of methane. So whatever is the molecular mass, same amount of the substance if you take, that mass is called 1 gram molecular mass. So how much is 1 gram molecular mass of any substance? Whatever is the molecular mass, same amount has to be taken in grams. So how much 1 gram molecular mass of water weighs? 18 grams. How much 1 gram molecular mass of carbon dioxide weighs? 44 grams. How much 1 gram molecular mass of methane weighs? 16 grams. Okay. But amazingly, these masses, that is gram molecular masses or molecular masses taken in grams, they all contain these many molecules. For example, 18 grams of water will have those many molecules, and 44 grams of carbon dioxide, which is 1 gram molecular mass of carbon dioxide, will have 44 grams of carbon dioxide will have these many molecules of carbon dioxide. 16 is the molecular mass of methane. So if you take 16 gram, it is known as 1 gram molecular mass, and 1 gram molecular mass, that is 16 grams of methane, is going to have those many molecules. Okay. So, we can take these masses, that is molecular mass taken in gram, as 1 mole. You know why? Because all these masses, that is molecular mass taken in gram, has these many molecules. And if you have these many molecules, the mass is called 1 mole, isn't it? So is gram molecular mass, that is molecular mass taken in gram, 1 mole? Yes. Why? Because if you take molecular mass amount in gram, it will always have Avogadro number of molecules, and whatever has Avogadro number of molecule, it is known as 1 mole. Okay. So whenever we talk about any substance, how much is 1 mole of that substance? How much is 1 mole of water? It is 18 grams, because 1 mole means Avogadro number of molecule, which is present in the molecular mass taken in gram, that is 18 grams. How much is 1 mole of carbon dioxide? 44 grams. How much is 1 mole of methane? 16 grams. Okay. So if 18 grams of water has got 1 mole, then how much is 36 grams of water? If 18 gram is 1 mole, how much is 36 grams? Is it not 2 mole? Because 36 is double of 18, no? 18 gram molecular mass taken in gram is 1 mole of water. So double of 18, 36 gram is going to be 2 moles. 3 times this, 54 grams is going to be 3 moles. So just now we found that 54 grams of water, which is 3 times 18, it has 3 moles. Can we also find that number of moles? How many moles are there in 54 grams of water with some formula, instead of just finding the multiples of 18, like 18 gram is 1 mole, and double of 18, 36 gram is 2 mole, and 3 times 18, 54 gram is 3 moles. Instead of finding the number of moles present in certain mass, can't we have a formula? And there's a formula like that. If you want to find the number of moles of any substance, when the mass of the substance is given, for example, they give you 54 grams of water and they ask you to find how many moles are there. So what you're supposed to do is simply take the mass of that substance out of which you're supposed to find the number of moles, and divide that with the molecular mass of the same substance. So this is 54 grams of water. We're trying to find how many moles are there in it. So I'll divide the given mass of water in grams by the molecular mass of water itself, which is 18. And this divides 3 times. And that tells you that there are how many moles? 3 moles of water in 54 grams. So I want you to learn this. I want you to know this formula for finding the number of moles. You see how we found the number of moles of water in 54 grams of water? We divided the given mass of water in grams by the molecular mass of water itself. So number of moles given by, what are you supposed to do? Mass of a substance, whatever substance is being discussed, mass of a substance has to be, and that mass of a substance must be in what? It must be in grams, must be divided by its own molecular mass. So when you divide mass of any substance by its own molecular mass, the way we did it here, we get the number of moles. So this is a very important formula. I hope most of you know this formula, but even if you have missed it, I want you to keep a note of this formula, that every time you're trying to find the number of moles of any substance, how many moles are there. So what you're supposed to do is just take the mass of the substance and divide by its own molecular mass. Okay. So now we have a formula for finding the number of moles, which is going to be N, which stands for number of moles, is going to be mass of any substance divided by molecular mass. Okay, now let's talk about solution. It's because this chapter deals with the solution. Let us try to understand what is a solution. A solution is nothing but a mixture. It's an impure substance. Because every time you prepare a solution, what you're supposed to do, you're supposed to at least take two substances and mix them together. Like for example, we mix water and salt. With only one component, it is not possible to prepare a solution. You have to have at least two substances, mixing together. So you can say that a solution is an impure substance. It's a mixture because it is prepared by mixing more than one substance. Most of the time our solutions are called binary solutions. Why binary? Because our solution will have two components, one solvent, another solute. Binary means something which has two components, solute and solvent. Okay. So in our solution, let's talk about a solution of salt in water. Let's say we'll be taking this sodium chloride. That's the common salt we use. So it's a solution of sodium chloride in water. You can prepare a solution of sodium chloride in water in so many ways. You can take 2 grams of sodium chloride and mix that in 1 liter of water. Or you can have another solution of same sodium chloride in water where you've taken, let's say, 10 grams of sodium chloride and added in 1 liter of water. Both these solutions are nothing but sodium chloride solution in water. You can have a third or fourth solution also like this, where you can add different amount of sodium chloride in water. So 2 grams dissolved in 1 liter, 10 grams dissolved in 1 liter, 15 grams dissolved in 1 liter. So you can have so many different solutions of same substance. So that means in a mixture, in a solution, you can have various amount of solute and solvent. The amount of solute and solvent can change, It is not necessary that every time sodium chloride dissolves in water that 2 gram has to dissolve in 1 liter. You can also have another solution of same sodium chloride where 10 gram dissolves in 1 liter. So that means in a solution, the proportion or the amount of solute and solvent can change. And that's why whenever we talk about a solution, we must express this, that in my solution, I've got this much of solute and that much of solvent. Unless you say that, if you only talk about a solution, it's quite meaningless. You know why? Because in your solution, you can have any amount of solute up to its solubility limit, any amount of solute and any amount of solvent. So if you only say that I have a solution of sodium chloride in water, it doesn't make complete sense, because you must say that in your solution, how much of sodium chloride is dissolved in what amount of water. And that expression, that way of saying that my solution has this much of solute and my solution has this much of solvent. What do you call that expression? That expression is called concentration of a solution. So what is the meaning of concentration of a solution? You see, so many times we have talked about concentration of my solution is so and so. What's the meaning? When you're saying concentration of my solution is so and so, you're trying to say that in my solution, how much of solute and how much of solvent is present. Okay. So that means we can measure or express the amount of solute or amount of solvent in a solution. But all these measurements or expression requires some kind of units, So to express the concentration of a solution, to say that my solution has so much of solute and so much of solvent, there must be ways, there must be units, So we're going to see few such expressions of concentration of a solution, few ways of telling that my solution has so much of solute and so much of solvent. That means we'll see some units of concentration of a solution. Okay. One of the first way we can express the concentration of a solution is called mole fraction. You see, there are so many ways we can express, there are so many ways in which we can express the concentration of a solution. You may have heard of those different terms, like we can do it in percent strength, we can do it in grams per liter, we can do it in mole fraction, we can do it in molarity, we can do it in molality, and we can do it in normality. There are so many ways, but because there is a constraint of time, so whatever is required absolutely in this chapter, we are only going to discuss those concentration terms. So the most important out here is going to be mole fraction. So what is mole fraction of a solution? It is a way of saying that my solution has so much of solute and so much of solvent, because you must say that. Unless you say that, your expression will not have complete meaning. So mole fraction is a concentration term. What is the meaning of mole fraction? Mole fraction can be defined as the fraction of number of moles of a component, fraction of number of moles of a component in a solution to the total number of moles of this, to the total number of moles of all the components, you can say, all the components in a solution. Usually our solutions will have two components, solute and solvent, but you know that it's also possible to mix 3 things to prepare a solution, or mix 4 things also, but such solution is going to be very complicated, so we're not going to deal with such a solution. We'll only have 2 components, solute and solvent. So let's say we have a solution or a mixture like that, where 2 substances are being mixed, A and B. A could be solute, okay, and B could be solvent. Or it doesn't matter also which one, solute and solvent. We can only say that there's a mixture or a solution where A and B are mixed together. So it's a binary mixture or a solution. While mixing A, or while taking A and while taking B to prepare this solution, let's say the number of moles of A is Na. Do you know how to find the number of moles of A? What are you supposed to do? I think you remember the formula which we earlier discussed. How do you find the number of moles of anything? When you divide the mass of A that you take with the molecular mass of A, you get the number of moles of A. In the same manner, right in the beginning while preparing this solution, you can also find out how many moles of B you are taking. Let's say you have taken Nb moles of B. Okay. So what is the total number of moles of all the components here? You've got Na moles of A and Nb moles of B. So the total number of moles of the solution is going to be Na plus Nb. Now what is the mole fraction of A? In this mixture, if you are trying to express that in my solution or in my mixture, what amount of A is there, you can do it in a term called mole fraction. And mole fraction of A is going to be the fraction of number of moles of A. So what is the number of moles of A you have taken? Na over the total number of moles of all the components. So you've got only 2 components there. The total number of moles of A and B taken together is going to be Na plus Nb. Okay. So when you divide the number of moles of any component in a mixture by the total number of moles of all the component, the fraction you get is called the mole fraction of that component. Similarly, how do you find the mole fraction of B? When you divide the number of moles of B, this time Nb, by the total number of moles of all the components, that is Na plus Nb, that fraction of number of moles of B over the total number of moles of all the component is going to be known as the mole fraction of B. So what is this mole fraction of A represents? It represents the amount or the proportion of A in this mixture. When A is in large amount, that means Na is going to be big. When A is in large amount, Na, that is number of moles of A, is going to be big, and naturally the mole fraction of A also is going to be big. So higher the mole fraction of A, what we understand that the amount of A in the mixture is large. If you have a mixture where the mole fraction of B is very small, which means the number of moles of B is small, that means there's very little amount of B present in the mixture. So expression of mole fraction therefore represents the proportion of A and proportion of B in the mixture. So this way you can express the concentration of a solution or a mixture in terms of mole fraction of components. Remember, fraction is always calculated out of 1. Like percentage is always calculated out of 100, fraction is always calculated out of 1. So what should be the sum of mole fractions of all the components? You've got only 2 components here, so if you add the mole fraction of all the components here in this mixture, the total must be 1. Like total of all the percentages in a mixture, let's say you've got two things A and B mixed together. If A is 25%, the B must be 75% because total of all the percentages of A and B together must be 100 because percentage is always calculated out of 100. Similarly, the fractions are always calculated out of 1. So the net sum of mole fractions of all the component must be 1. And we can prove that if you add these two mole fractions, then the net sum is going to be 1. Let's see. What is XA? Isn't it Na by Na plus Nb? It is. And what is XB? That is mole fraction of B. Isn't it Nb divided by Na plus Nb? So these are the mole fractions of A and B. So let me find the LCM of denominator, which is going to be Na plus Nb because it's same both sides, and then this cancels and divides, so there will be Na left and Nb there. So both these cancels and the sum is going to be 1. So I told you that the mole fraction, the sum of mole fractions of all the component in a mixture must be 1. The way the sum of all the percentages is always equals to 100. Okay. So this is the first expression of concentration, that you can express the concentration of your mixture or a solution in terms of mole fraction of solute and mole fraction of solvent. Okay. In this chapter, all the properties of solute are given this suffix 2. Whatever belongs to solute is marked as 2, like weight of the solute will be written as W2. Molecular weight of the solute will be written as M2. Similarly, the mole fraction of the solute will be given as X2. That's the, some kind of rule here in this chapter. So all the properties of, all the variables of solute are marked with 2, and all the variables or properties of solvent is marked as 1. So if you follow that convention, it's going to be easier. After completing the discussion on the mole fraction, now let's talk about the another concentration term that is also important in this chapter. And that concentration term is called molarity. So what is molarity? Molarity is also a way of telling that my solution has so much of solute and so much of solvent. So it's an expression of concentration. So what is molarity? By definition, molarity is the number of moles. So you all know how to find the number of moles. To find number of moles of anything, you have to divide its mass by its own molecular mass. So number of moles of solute, number of moles of solute dissolved in 1 liter solution. Remember, it's not solvent, it's 1 liter solution. 1 liter solution means what? Means this 1 liter will have both solute and solvent together. It's not 1 liter solvent, it's 1 liter solution. For example, okay, let me take this acid. All of you know this acid with the formula H2SO4 is called sulfuric acid. So that's its molecular formula. So let me add the masses of all the atoms present here. There's one hydrogen. So you see what I'm doing? I'm trying to find the molecular mass. So hydrogen is there, its mass is 1, there are 2 of them present. Sulfur's atomic mass is 32, let me tell you. Oxygen's mass, you know, is 16, but there are 4 atoms. So if you add the masses of all the atoms present in the molecule of sulfuric acid, the net mass is going to be 98. So that's the molecular mass of sulfuric acid. Okay, 98 is the molecular mass of sulfuric acid. And you know that whatever is the molecular mass, if you take that in grams, it's known as 1 gram molecular mass, and is also known as 1 mole because it contains Avogadro number of molecules. So 1 mole of sulfuric acid is nothing but its molecular mass taken in grams. So remember, if you have 98 grams of sulfuric acid, it's going to be 1 mole. Okay. So I have over here a measuring cylinder, which is used for measuring volumes of liquids, you know. So there's a measuring cylinder and there are markings here to find the volume of liquids poured in it. So let's say this is a mark for half liter, 500 ml, and this is the mark for 1 liter. So what I'll do is I'll be taking 98 grams of sulfuric acid. Why 98 only? Because I know that its molecular mass is 98. So if I happen to take 98 grams, whatever is molecular mass, that amount in grams, I know it's going to be 1 mole. Why I'm so concerned about the moles? Because molarity is nothing but the number of moles of solute dissolved in 1 liter solution. So I require number of moles to find the molarity or to express the concentration of my solution in molarity. And that's why intentionally I have taken sulfuric acid, that also how much? 1 mole. Okay, that is molecular mass taken in grams. So here I have 98 grams of sulfuric acid. That is 1 mole of sulfuric acid. Now, after adding sulfuric acid, I'll start adding water to it. So I'll add water now. So that means now water and sulfuric acid is getting mixed. So it's a solution of sulfuric acid and water. So if you keep on adding water, the volume will come up to this. After that, I'll stop adding water now because the volume has reached 1 liter. Is this 1 liter of water? No, it is not 1 liter of water because before adding water, I have already added sulfuric acid. So it is 1 liter of the solution. Okay, it's a 1 liter of a solution because it has got water and sulfuric acid both present. So I have 1 liter of solution. And in this 1 liter of solution, how many moles of sulfuric acid is present? Because sulfuric acid is solute here. So how many moles of solute or sulfuric acid is there? 1 mole, because I added 98 grams, that is molecular mass taken in grams. So in 1 liter of the solution, I've got 1 mole of sulfuric acid. And whatever number of moles of the solute is present in 1 liter solution, that is going to be the concentration of this solution in molarity. So molarity is going to be 1. It's called 1 molar. Why is it 1 molar? Because in 1 liter solution, I've got 1 mole of solute, that is 98 grams of sulfuric acid. So that's the meaning of molarity. Molarity is the number of moles, whatever number of 10 moles, 5 moles, whatever number of moles of solute you've got in 1 liter solution, that's known as molarity. Okay. For example, if you've got 10 moles of sulfuric acid here in 1 liter solution, the molarity or the concentration of the solution is going to be 10 molar. Okay. So this is how one can express the concentration of a solution in this next term called molarity. But the problem with the molarity is that every time you try to express the concentration of your solution in molarity, you have to have 1 liter solution. If you don't have 1 liter solution, then you will not know how many moles are present in 1 liter. But it's not always possible to prepare 1 liter solution. What if you don't have 1 liter solution? You've got only 100 milliliter of a solution. You've got only 250 milliliter of a solution. So isn't it possible to express the concentration of that little bit of solution also in molarity? There should be a way out, because as per the definition, whatever is the number of moles present in 1 liter, then only that number of moles called molarity. But if you don't have 1 liter, then you get into trouble, because then you'll not know how many moles are there in 1 liter, then you'll not be able to express the concentration of the solution in molarity. So what is the way out? The way out is to have a formula, to have a relation with which we can find the concentration of any solution having any volume, need not be 1 liter, in terms of molarity. So that's what we'll try to do. Though this derivation is not part of our syllabus, we are not required to derive, but still you should understand how do we get this formula for finding the concentration of a solution in molarity. So how do I do that? I'll assume that I have V liter of solution. I've got V liter of solution. By taking V liter, I have broken that constraint of 1 liter. I need not have 1 liter. I can have any amount. That's why I've taken V liter. This V could be half liter, 1/10 of a liter, or 20 liter. V can represent any volume of the solution. So I've got V liter of the solution. And that V liter of the solution dissolves, let's say, W grams of solute. Okay. So I've got V liter solution, any volume of the solution, and has that many grams of solute dissolved in it. So that's the mass of the solute dissolved in V liter solution. But you know that the mass of the solute is not going to give me molarity. Molarity is not about the mass of the solute. Molarity is all about the number of moles. So if I just put the mass there, it's not going to give me concentration in molarity. So I need to somehow convert this into number of moles, because molarity is the number of moles of solute. So how do you convert this into number of moles? What you can do is you can simply divide this mass with the molecular mass, isn't it, of the solute. You know the mass of the solute you've added, W grams. So what you do is divide that mass you've added in the solution with the molecular mass of the same solute, and that mass by molecular mass is going to give you what? Isn't this number of moles? Yeah, that's how we find the number of moles, by dividing the mass of any entity with its molecular mass. So this is going to be the number of moles of solute. So I've got V liter of the solution. Within that, W by M moles of solute is there, mass by molecular mass, which is number of moles of solute is there. So is this number of moles of solute the molarity of this solution? No, because this is the number of moles of solute present in V liter. But number of moles of solute present in 1 liter is going to be molarity. This is not 1 liter, this is V liter. So if V liter has that many moles, can't you find 1 liter will have how many moles? Because it's going to be a simple unitary method problem. So V liter has that many moles. 1 liter will have how many moles? So it's going to be W by M divided by V. Yeah, this V goes there and divides. So that's the number of moles of solute dissolved in 1 liter, isn't it? And whatever is the number of moles of solute dissolved in 1 liter, according to definition, that is going to be the molarity of this solution, or the concentration of this solution in molarity. So I've got these many moles in 1 liter, and that number of moles in 1 liter is molarity. So what's the formula molarity? We saw formula molarity is W by M by V. So let's see what is this W. W is the mass of the solute dissolved, but since mass is not going to give me molarity, so I have to divide the mass of the solute by the molecular mass of the solute, and that gives me the number of moles of the solute. So number of moles again is divided by the volume of the solution in liters, because number of moles divided by the volume of the solution in liter gives you the number of moles in 1 liter, and that's why it is known as molarity. So why in the expression of molarity, why in the formula molarity, there is mass divided by molecular mass to get the number of moles, because molarity is number of moles. And why the number of moles again divided by the volume of the solution in liters, because we have to supposed to get the number of moles present in 1 liter. That's why this volume goes and divides. So that's the formula of molarity. Sometimes the formula molarity is also modified and written as N by V. Is this right? This is right. Why? Because mass by molecular mass, can't you write that as number of moles? So W by M I'm writing as N, number of moles, and then divided by V. So that's how molarity is found. Okay. Now, since two of the expressions of concentrations are over, mole fraction and molarity, we'll head for the third one. And this expression, the third way of expressing concentration, is called molality. It's not molarity, it's molality. So what's the meaning of molality? Molality is also a way of saying that my solution has so much of solute and so much of solvent. So it's an expression of concentration. So molality is what? Molality is also number of moles of solute. Exactly like molarity, which is number of moles of solute, molality is number of moles of solute dissolved in 1 kg, or 1 kg means how many grams? 1000 grams of solvent. So the difference here is molarity is the number of moles of solute dissolved in 1 liter solution. We had 1 liter solution containing both solute and solvent. But here molality is the number of moles of solute dissolved not in 1 liter solution, but only 1 kg solvent, okay, or 1000 grams of solvent. So what's the meaning of that? Let me explain the meaning of that. You see, right in the beginning you are supposed to take 1 kg solvent. So I have taken 1 kg water, that is 1000 grams of water. So it's not 1 kg solution or 1 liter solution, only 1 liter solvent. So directly 1000 grams of water I have taken. And to this I'll add 98 grams of sulfuric acid. You already know from our previous discussion that 98 is the molecular mass of sulfuric acid. So the molecular mass taken in gram is going to be 1 mole. So I've taken 1 mole of sulfuric acid and I've dissolved that in 1000 grams of water directly. Okay. So when you add that 98 grams, the mass is going to increase. It's going to be more than 1000, because 1000 plus 98 is going to be 1098 grams. Okay. So I have added 1 mole of solute in 1 kg solvent. And whatever number of moles of solute is there in 1 kg solvent, that's known as molality. So the molality here is 1. I can write this as 1 molal. You see, molarity is expressed as capital M and molality small m. Okay. So that's how the concentration of a solution is expressed in molality. You see, if you add 2 moles of this in 1 kg, then the molality is going to be 2, because molality is the number of moles of solute in 1 kg solvent. Okay. So if you add 1 mole of sulfuric acid, molality is going to be 1. If you add 10 moles of sulfuric acid in 1 kg solvent, the molality is going to be 10. Again, there is a problem here, exactly like molarity. The problem is that you have to have a solution prepared by dissolving certain number of moles of solute in 1 kg solvent. It's not always possible to take only 1 kg solvent, you know. Sometimes if you are preparing a little bit of solution in a test tube or in a volumetric flask, so it's not possible to always take 1 kg of solvent. So what if you have prepared a solution which does not have 1 kg of solvent dissolved in it, you know? Then how do you calculate the concentration of your solution in molality? So there must be a formula exactly like molarity. Okay. So we're trying to find the formula for molality. The formula is going to be like this. First look at it. See, I've got W1 grams of solvent. Earlier I started, in the case of molarity, I started with V1 liters, because there the volume of the solution was required. Here there's no volume anywhere. You see, number of moles in 1 kg, so there are only masses. So I've taken W1 grams of solvent. By taking W1 grams of solvent, I'm breaking that barrier, that constraint of 1 kg. So I'm saying I don't have 1 kg, I don't have 1000 grams of solvent, I have got W1 grams of solvent, which could be 10 grams, 20 grams, 100 grams, 1000 grams, any amount. So I've got W1 grams of solvent, and let's say that dissolves W2 grams of solute. So W1 grams of solvent, I told you in the beginning, all the properties of solvent are marked as 1. There will be 1 suffix given to all the properties of solvent, and all the properties of solute are marked as 2. So I've got W1 grams of solvent dissolving W2 grams of solute. But soon I realized that the mass of the solute, W2 grams, is not going to give me molality, because molality is not the mass, molality is the number of moles of solute. So this mass of solute, can you convert into number of moles? Yes, you already know how. You just have to divide this mass of solute by the molecular mass of the solute, isn't it? Then that gives the moles of solute. So you understand why we are dividing the mass of the solute by the molecular mass, because that gives the number of moles of the solute, and that's what we need, number of moles of solute, to express the concentration in molality. So is this number of moles of solute dissolved in W1 grams of solvent molality? No. According to this, number of moles dissolved in 1 kg is molality, but this number of moles dissolved in not in 1 kg but in W1 grams, isn't it? So this is not going to give me molality. So what I'll do is, if W1 gram has that many moles, then 1000 gram will have how many moles? If you have 1000 grams, I can simply find using unitary method. So W1 has that many moles, 1000 will have how many moles? What do I do there? I take this W1 the other side and divide, and then 1000 goes and multiplies, isn't it? That's how unitary method is carried out. W1 divides there, 1000 multiplies. So I have the number of moles of solute here that is dissolved in 1000 grams of solvent, and number of moles of solute dissolved in 1000 grams of solvent is molality. So that's the molality. Okay. So what's the formula of molality now? So molality is going to be W2 by M2 divided by W1 and multiplied by 1000. So let us analyze this formula of molality to understand why the formula is like this. Why there is W2 by M2? Because W2 mass of the solute, when you divide by the molecular mass of the solute, you get number of moles of solute. And that number of moles of solute, when divided by the mass of the solvent and multiply by the 1000, you get the number of moles present dissolved in 1000 grams. and number of moles dissolved in 1000 grams is called molality. So each and every component of this formula has some meaning, you know. Why mass of the solute is divided by molecular mass to get the number of moles, because number of moles of solute is required as per the definition. And why the number of moles of solute is again divided with the mass of the solvent and multiplied by the 1000, because when you divide that number of moles with the mass of the solvent and multiply with 1000, you get the number of moles dissolved in 1000 grams. That's known as molality. Okay, so this way we have another concentration term introduced here, is called molality. But in exam they can ask you this. In fact, I remember this kind of question had come on once in our exam. The question will be, if you already have molarity, which you calculate by dividing the mass of the solute by molecular mass divided by the volume of the solution, why do we need molality? What's the need of having molality? You can always express the concentration of your solution in molarity. Then why to have another unit or another expression of concentration? The reason why molality is here is molarity depends on the volume of the solution. There is this volume of the solution here. And volume of solution or liquids tend to expand or contract with the changes in temperature. When the temperature rises, volume starts expanding. So volume increases. And when the temperature decreases, volume contracts. So that's why when temperatures are changing, molarity is going to get affected. What is the meaning of that? If you calculate the concentration of your solution in molarity, out here in Darjeeling, where the temperature is low now, and take that solution somewhere else where the temperature is high, then the molarity is not going to remain same. You've got to recalculate the molarity there, because molarity changes with the change in temperature. Why? Because with the change in temperature, the volume expands or contracts. So when the volume of the solution itself changes, the molarity also changes. So that's why molarity is sensitive to changes in temperature and pressure. So we needed a concentration term which is not affected by changes in temperature and pressure, and that's why we have molality. Look at the formula molality. We've got only masses everywhere. Mass of the solute, mass of the solvent, molecular mass of the solute, and multiplied by 1000. So there is no volume involved anywhere. So because of that, whether you calculate the molarity of the solution here in Darjeeling or in any other place where the temperature is different, this amount, that is the concentration calculated in molality, is not going to change with the change in temperature. It remains same. And that's why molality, you can say, is independent of changes in temperature, is not affected by the changes in temperature. And that's why it's so special way of expressing the concentration of a solution. So that way we have finished discussing different aspects of concentration terms, like different ways of expressing concentration. Now we can start this chapter properly.